Everybody, sorry we're off to a late start. I had some firefighting to do this morning. Today's lesson is really kind of self-explanatory, and I don't want to go through the whole thing. I'm happy to take questions about the lesson. So what we do in today's lesson is we go through Sudoku, and we kind of do it from start to finish, and do the whole shebang. And that turns out to be a huge amount of fun. I hope you guys enjoy going through that content. It was fun to record because it's a case where we're able to solve a more complicated problem by building up our solution from these smaller pieces that really at this point should be familiar to us. There's nothing in the code that I wrote for this particular lesson that is new to us, but it's sort of like what we're going to start to do, and we're going to do this over the course of the rest of the semester, alongside learning some new concepts and ideas. We're also sort of starting to build up longer chunks of stuff. So if you took all the code that we wrote in the different parts of this lesson and kind of strung it together, it starts to add up. But it's a set of very simple steps that are, we're just kind of placing one after another. So that's the sort of approach behind today's lesson. I'm here, a couple of you guys are here, so there's stuff you want to talk about, throw it up in the chat. I'll also jump over on the lesson thread in case people want to ask stuff there. Ooh, I like that term, ragged arrays, yeah. But anyway, so if you guys have questions or things you want to chat about, I'm here. Like I said, I don't have a lot of stuff to add to this particular lesson because it's, I think it speaks pretty well for itself. But I'm happy to take questions about the lesson itself, about the homework, about some of the choices, sort of design choices that we made throughout today's lesson, or sort of whatever you guys are interested in discussing at this point. So let me know. I will hang out. Keep an eye on the chat. Maybe we'll see if anybody. Let's see here. Grab a link to this to put up in the chat. Scroll down a little bit here. We'll look at the problem we're solving. Taking requests. Anything you guys want to see explained? Any stuff you want me to go over? I'm here. And if there isn't anything, that's cool too. We can just kind of hang out. Thanks. It's a beautiful day here in Champaign. It's a nice day. I'm a big fan of the cooler weather. Maybe that's because I was born during this time of the year, but I'm always looking forward to fall. Never lasts long enough, but it's nice that it's here finally. So get out for a walk later and enjoy the sunshine and the cooler temperatures. I have a hoodie on, the hoodie that you'll see on a regular basis for the rest of the semester. So life is good. Thanks again. Do you guys have any questions? Come on. I mean, I can't be doing that good of a job at explaining things. Or I shouldn't say just me. I mean, the course staff can't be doing that good of a job at explaining things. You guys must have things that you're curious about. So feel free to ask away. So maybe since nobody is asking questions, I'll just start rambling because and we'll come back and I'll get a chance to ramble about this later in the class. So Sudoku is kind of an interesting problem because, and we'll talk about this again later when we talk a little bit more about algorithms and some of the theoretical aspects of computer science. We don't get into theory really in any meaningful way in this class, but I like to talk about it to sort of pretend that I'm smart and I understand this type of stuff. But so there is there's a class of problems in computer science that are known to have the following characteristics. So they're known to be very hard to solve, but very easy to validate that the solution is correct. And so, you can think of it taking, particularly as the problem gets larger. So think about trying to do a larger version of Sudoku, like not just the 9x9, but we could, you can expand Sudoku, right? So you go to a 3x3, and then you can go to this 9x9 grid, and then you can expand it out, and then there's larger variants. And as the size of the board gets larger, for a given initial configuration, the problem gets harder and harder and harder to solve. However, as we pointed out in today's lesson, verifying a solution is extremely straightforward. I mean, it's some programming, and so we had some fun with it, but it's not difficult from an algorithmic perspective. It's very straightforward. Just kind of go down the rows, check, 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 across the columns, check, 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 right into each box, and so that's how it works. But this category of problems is really of deep interest to computer science. The primary open question in theoretical computer science, and it's been open for a long time. And this is one of those questions that, many extremely intelligent people have labored over. I'm sure I knew somebody personally who had, a story of the time in his life where he spent, 2 years in his basement trying to work out a solution to this particular conjecture. So this is this question of whether P equals NP. You might have heard this come up in computer science conversations. At the real root of this question is this fundamental question about the universe. So on some level, technology is a field where we don't always get to interrogate the universe. I mean, computer science is an interesting field in the sense that computer scientists are studying things that we created ourselves, right? That's sort of a weird thing. Like a physicist studies the world around us, as do chemists and biologists. They know, biology doesn't create a universe and then study it. Most other scientific disciplines and even the humanities disciplines operate in this way, right? I mean, they study things around us. Computer scientists do that too, but they also we've created these things, right? And so on some level, some of it's like a little self-referential, right? Like, oh, okay, well, the computer works that way because we wanted it to work that way, or because there's certain electrical characteristics that caused it to need to be that way. But there are, even amidst all of this, all of the technology and the wires and the circuits and the transistors and the computers themselves and the processors and the memory and the networks and stuff like that, all the stuff, there are still these deep conceptual concerns at the core of computer science. And really it boils down to problem solving. You can, and theoretical computer science has abstracted the notion of computation away from a computational machine. So there are people that kind of study the idea of computation in the abstract. And if you go on and take theory courses in our department, you'll learn a little bit about this. I remember years ago taking a theory course at Harvard when I was there, and really actually enjoying it. I'm not a theoretician. I don't do theory. I'm much more of a practitioner, but at the same time, presented really well. This is really interesting stuff to think about this idea of kind of an abstract computer. In fact, one of the earliest computer pioneers, a woman named Ada Lovelace, was actually engaged in this type of exploration of sort of this abstract idea of computation, mainly because she was working hundreds and hundreds of years, well, maybe not hundreds, but like at least 100 years before we actually had a real computer. So there were people, even back then, this is like the 1800s, they're already dreaming of, what could we do with this abstract machine that could solve all sorts of different types of problems. Anyway, the point is that at its heart, computer science, considers these, well, I shouldn't say its heart. Its heart is also like the wires and the cables and all the good stuff. It's one of the things that's fun about this field is it brings together people with like really divergent interests and worldviews. It has this beautiful mix of theory and practice that I think you don't find in every other field. Like physics, has people that are experimentalists and build cool stuff, but not every person, I shouldn't say every person, a large chunk of the people on the planet now have this product of computer science in their pockets and are using the internet, and so are really experiencing the fruits of this, right? Scientific discovery is important on its own terms and for its own good, but at the same time, being able to build things is really neat. Anyway, so at the same time that we're building things, we're also wondering about how we can solve problems. And there's this deep question in computer science about whether there are certain problems that are just really much harder to solve than others, or alternatively, whether or not humans have just not found the right ways to solve these problems, right? So those are two potential hypotheses. One hypothesis is that there are some problems that just can't be solved efficiently. They can be solved, there are algorithms to solve them, but the algorithms are poor. The algorithms are slow and they take a long time to come to a solution. The other hypothesis is that we just haven't found the right algorithms to solve these problems yet. And so that's a really interesting tension, right? Are we the problem? Did we just not come up with the right, solution, or is the problem really fundamentally very difficult? And I think, if you ask theoretical computer scientists, I think there's a lot of sort of experiential evidence for the hypothesis that there is this group of problems that are very, very difficult to solve and are just different than other problems. Part of the reason for this is that these problems actually have a lot of similarity to each other. So there's a group of problems, I don't know how many are in it, where you can essentially show that if you can solve one, and when you originally describe the problems, they sound different, but it turns out that if you solved any one of them, so the traveling salesman is an example of one of these problems. If you solved any one of these problems, you could efficiently solve all of them. So they all have this self-similarity to them, and they're kind of all one instance of this bigger problem. So what theoretical computer scientists have been trying to do for a long time is prove, not just, not just an argument based on, well, we haven't figured out how to do it yet, because that's not a proof. Actually prove that this category of problems is different. And so far, no one has been able to do this. And there are, multiple large financial prizes at stake. This is the type of thing that will, immediately enter somebody into the, I don't know, there's no Nobel Prize for math, but there's something like the Fields Medal or something like that. I mean, the person who solves this problem you will read about it, right? This will be on the front page of the papers. This will be in the press. It's such a big, old, important, interesting problem to computer science that when it finally is, solved, everybody around the world will hear about this, and the person that did it will be incredibly famous. So anyway, all to say that Sudoku turns out to be more interesting than maybe you thought. And who knows? I mean, maybe the person that's actually going to address this conjecture is working on it right now. I don't know. Maybe I'll send out a link to this article later on the forum. I always enjoyed this story. There was a problem in mathematics that had been open for a long time, and it's one of these sort of old famous math problems that many people had attempted and nobody had been able to quite figure it out. And then out of the blue, there was this. Actually, I think he was like an adjunct professor at a school out east. I can't remember exactly what school it was. Who, submitted a paper to this mathematical journal claiming that he had solved this problem. And, with these type of open problems, you get lots of people doing this, and a lot of them are cranks, and they're just sort of crazy, and they're wrong. But, the article about this goes into the fact that when the reviewers actually started to examine this, they got very excited because they were like, this is legit. And so rather than just sort of dismissing it, even though they had never heard of this person wasn't a famous mathematician. But, as they started to go through it, they couldn't find any flaws. They sent it out for further review, and it turned out that the guy had actually solved the problem. And, he's the kind of person that's very happy to work quietly. The articles about him say that, he enjoys, not having, he's actually, so this is one of the parts about the story, he was actually teaching like intro calculus at some university, just to kind of make money and for something to do. And imagine you're taking this class and you're thinking, oh man, who is this guy that's teaching it? It's just some random dude that the university assigned to teach my Calculus 1 class, and it turns out to be somebody whose name is all over the papers a couple months later because he proved this conjecture. And so I always like that sort of story, right? And also I sort of like the idea of people having this long engagement with a single problem and really sort of digging into something and having a passion that they allow to kind of guide them and orient some of the course of their life. So that was a cool story. There's a funny part of it where he was talking with his wife. I guess they have this long distance relationship that they've maintained for a long time. And she said, and he told her, oh, well, my name might be in the papers, because this was when they were about to start publicizing the results. And she was like, are you drunk? She thought he was nuts. But anyway, he was right. His name was in the papers. And, so anyway, I don't have, much more to say about the lesson other than, now that I'm done rambling about the Sudoku parts, which are sort of neat. But again, this is the kind of example of the stuff that we'll be doing going forward in this class. The rest of the week, I'm going to sign off in just a minute, get a little bit of an early finish to today's lesson because there's not too much to talk about. The rest of the week is going to be a lot of fun. We have some really cool topics coming up. We're kind of at the point where we're going to do kind of two things at the same time. One is give you more practice with just developing your own simple algorithms and getting used to some of the patterns that we're developing for solving problems. The other thing is talking a little bit, and this is not a big part of this class, but we're talking a little bit about what's going on under the hood. Like what actually happens when you run Java code, because there's actually some things that as a computer scientist and programmer you want to know about that. For now, up until this point, we've been just sort of letting you guys play and experiment in playgrounds, and we haven't been super clear about exactly what steps are taking place. But having that conversation, which we'll do tomorrow, is actually going to deepen our appreciation for what's happening, some of the sophistication involved, and then also help you with dealing with error messages that you might encounter. And we'll also talk about some new Java features, which is pretty neat. We're actually, the playground examples in this class are all using the latest version of Java, which is Java 14. I think that came out 6 months ago. And there's actually some kind of neat new features that are included in Java 14 that we can talk a little bit about. We'll talk about one of them on Thursday. And then on Friday, we'll talk about testing. So we'll actually have an entire lesson just focusing on, what is software testing? How do you do it? What's some of the intuition behind it? How can you use it? And use a testing mindset when you're going through your own code to be able to write better code. So don't you make a Sudoku solver in 126? So you can solve simple, that's a great question. So you can solve simple instances of Sudoku fairly efficiently. There are algorithms, I think, to do the 9x9 board. That's not particularly hard. Keep in mind something else. So the part of what's fun about these complex computer problems is how quickly they get hard. But small instances of most problems are usually easy to solve. So sometimes you can solve them in what's known as sort of a brute force approach, right? Where I just literally try everything until something works. In other cases, there are more sophisticated algorithms that, what you can show will eventually produce a solution even if they're not optimal. But for very, very small instances of almost any problem, computers are just so powerful right now that you can solve them quickly. This is also true for stuff like encryption, right? So one of the things that you've seen, and you guys will probably continue to see throughout your lifetimes, although the pace of computer speed increases has started to taper off a little bit, which is an interesting story in and of itself. But the idea is that as computers have gotten so much faster, certain things that used to be slow have gotten fast enough to do that we've had to make them harder, right? This is particularly true in computer security. So the encryption approaches that we use for, I'll come to that question in just a sec. The encryption approaches that people were using in the past relied on certain things being difficult to do. And as computers got more and more powerful, those things didn't look so difficult anymore, right? And encryption in many cases is all about time, right? An adversary would always be able to decrypt your message, but if it took all the computing power in the world and you had to wait 10 years, not practical, right? Particularly for sort of like sensitive communication, right? I mean, again, if somebody can rent a machine on Amazon and figure out my credit card number after running that machine for 100 years, I'm cool with that. We'll use an IDE instead of playgrounds. No. So throughout all the homework that we're going to do in the class, all the lesson content is going to be done on the playgrounds. Well, we may drop a few videos where, like for tomorrow's lesson on compilation, where we do a little bit really at the command line, actually. We will use an IDE in this class for the machine project. So you guys will be doing that in Android Studio. So if you're an IDE person or an IDE junkie, like you'll get your fix. That's coming up. The reason for this, to be honest, is that as useful as IDEs are, and I use them for the projects I work on, like most normal people. They also encourage some bad habits, particularly when you're getting started. So, if you can't write a small piece of code without relying on what's an IDE? An IDE is a program that helps you write code, and you're going to get familiar with this. This is called sometimes the acronym is for Integrated Development Environment, and what that means is that usually this is a program that allows you to edit code and helps you do that through nice formatting and keyboard shortcuts, and then also allows you frequently to build things. And the idea behind integrated development environment is that it's doing a bunch of these things. So for example, when you guys start using Android Studio, you're going to install a piece of software on your computer. You'll type your code in there, but there'll be a button that actually allows you to run the code in an emulator, right? There'll be other buttons that do other fancy, complicated things. So it's really kind of an entire program that's designed around the task of building software. So, you imagine Android Studio, for example. Android Studio is an entire program that's built around the idea of doing one thing, building Android applications. Now, those applications could be anything. That's up to you and your creativity. But the program that you're going to run on your computer is designed to really just enable that one type of software. And there's a bunch of different IDEs out there for different things. As you go on in computer science, you'll use different ones at different times. They're not required. There's other ways of doing things that don't use them, but they are, at this point, I would say, I used to be a little bit anti-IDE, but I've come around. They're very helpful for doing certain things, and you sort of get used to them. But anyway, going back to going back to why we encourage you guys to do things in these playgrounds, both on the quizzes and on the homework. It really is to start to be able to develop some good habits, right? So, being able to type your code without lots of shortcuts and, things like that. Being able to keep your code looking reasonably decent without, reliance on auto formatters and things like that. So the homework environments are going to be the same kind of throughout the rest of the class, and that'll also be true on the quizzes. We've never used an IDE for any of these small problems, and we won't, because I don't think it's appropriate. For Android, like I said, Android Studio is what we use because that's what people use. I'm happy to answer any questions. If you missed your chance to take the quiz this morning, try to find, and if you have time later today, just feel free to join one of the other Zoom links. I think that sort of test this just quickly. I think that the issues with the website have largely stabilized, and so we're going to keep an eye on things. But we'll also, if you're super busy today and jammed up, we can also make some TAs available to proctor quizzes tomorrow. I'm pretty sure maybe we'll turn some of our normal daily sessions into quiz proctoring. I apologize for that. It's a new system. Obviously, first time you deploy something, there's frequently some bugs, and to be honest, I'm surprised it wasn't worse. But I think, fingers crossed that we have things sort of the fires down to embers, and we're keeping an eye on stuff moving forward. One of the things that's happened, to be honest, is that the sophistication of the web tools that we use for this class has increased a great deal, and so we're still sort of figuring out how to support that in the best way. We actually have CS125 runs our own private cloud, so we have about 24 machines sitting around somewhere in some data center on campus that we use to provide the back end for this class. So those that you will take another quiz next week, but you know you're free to. You should take today's quiz today or tomorrow, right? And so you know we're the yeah. I mean, you know, I'm not trying to break anything, but when you move fast, when you move fast, things tend to break. This isn't, you know, this wasn't a thing until today, so it's not broken quite yet. I'm sure at some point we'll break it again and put it back together in a slightly better way. But for now, we're just going to try to keep it online. Yeah. So please, you know, take quiz 3 at some point soon, right? If you can't today, you're welcome to join another Zoom session. Otherwise, tomorrow. Next week, we're going to run, you know, another quiz. It actually is a midterm, so it's not droppable. That's cumulative up to this point. Same platform, and by that point, I think we'll have more of the kinks worked out. So, but for today, I haven't had a chance to communicate with the TAs yet. I'll do that in a minute. But you know, if you can, feel free to come by this afternoon and take the quiz, or this evening. We have sort of labs that go until 8 p.m. All right. If there are other questions, let's see, I'm going to scroll back up here about stuff. Doesn't look like there are. I'll stick around for a minute just to see if there's any lingering questions or issues people want to discuss. Otherwise, I will look forward to seeing you guys tomorrow, where we do have a fun lesson. And tomorrow will be actually a neat chance for me to do a walkthrough, because I can show you a little bit of stuff under the hood, and you guys can ask questions about what's going on, because tomorrow is our first chance to kind of like get into the mind of Java, right? And try to figure out what's actually happening when we run our code, and there's some interesting things that are going on there. So I'd be happy to help demo that in our daily walkthrough. Please take the quiz today if you can. I don't want people taking it tomorrow. I mean, it's not fair to other students. So, you know, we know when you take the quiz. You know, I do think that the students this morning that were obviously affected by the problems we're having, those students we're going to accommodate. But if you need to take the quiz during your lab time, you know, again, it's just, you know, it's not fair to other students to allow you to take the quiz later with more time to prepare. So, all right, I will see you guys